Okay, thanks everybody for joining us. We seem to have got everybody in now. So good morning. Thank you for joining us. As we can see today, the subject of the webinar is going to be Modbus and Modbus TCP communication. We've got a video first of all, which is roughly 25 minutes long, and then we'll go into a question and answer session. So if you've got any questions that come up during the webinar, then please type them into the questions box in your control panel there, and then we'll come to those at the end of the video. So let's get started.
Hi, in today's tutorial we will be running through Modbus and Modbus TCP communications. We'll first talk about what Modbus is. We'll talk about the Horner OCS in Modbus TCP server mode and in TCP client mode. We'll go through configuration and programming, and we'll finish with a live Q&A session. So, what is Modbus? Let's go through some background and protocols. Modbus was invented in the late 70s by Modicon. It's the most common and popular industrial protocol for device-to-device communications. It can be used with a variety of different physical media. It can be used over radio, over old-fashioned serial ports of RS-485 and RS-232, and it can be used over Ethernet. It's popular largely due to its longevity, versatility, and simplicity. Modbus is very easy to understand. It's organized around 4 different types of memory areas, which are patterned after traditional PLCs. There are coils patterned after digital outputs, inputs patterned after digital inputs, and input registers, which are analogous to analog inputs, and holding registers, which are analogous both to analog outputs as well as internal general-purpose analog type registers. Its addressing scheme is 1-based, so coil address numbers go from 1 up to 10,000. There's a capacity for 10,000 with the traditional 5-digit addressing scheme. Let's talk about how the Horner OCS can be set up both as a Modbus server or a Modbus slave, and later we'll talk about it as a Modbus master. If I'm going to be accessing data from an OCS over Modbus, what Modbus registers or references should I use in order to access OCS data? Retrieving OCS registers over Modbus is easy because we make our underlying OCS registers evident. Lots of our customers still use the traditional memory-based register structure, where every time they create a variable in their program, they map it to a specific memory location. Due to this, they are aware of what memory locations are being used for which variables, and there is a standard published OCS register map to Modbus register. On the left, you see all the different OCS memory types, and the range in which they are supported over Modbus. The third column shows the Modbus reference address. The fourth column shows all the different function codes that are supported in the OCS, and the last column talks about the offset. The master makes it easy for you to specify a function code and an offset. There's a variety of ways in which you can access general purpose %R registers. Those are all in the bottom of the chart, and that's partially because of an evolution. If you have the ability to use the 6-digit Modbus reference instead, that gives you access to the most %R registers. 10,000 of them, starting at 410,001. You've got 2 different approaches for accessing these OCS registers, using the Modbus references or using the function code in combination with the offset. Use whichever is convenient, as they all point at the same OCS register space. Let's talk about configuration, which I'll demonstrate later. Configuration of an OCS as a Modbus TCP server is simple. You have to configure your Ethernet, so you need your IP address, netmask, etc. If you want to support the OCS to reply to OCS queries that come in, then you check the Modbus slave checkbox under Resident Protocols. You also have additional options that are available under Configure Selected Protocol, where you can use UDP instead of TCP over Ethernet. You can also change your port number, although it's not recommended. You can assign a write protect bit, so when that bit is on, it prevents any data from being written over Modbus. The other ways of preventing any data from being written over Modbus are to not support the protocol by not checking the Modbus slave block. Let's talk about configuring the Horner OCS as a Modbus serial slave. We're talking about the OCS responding to Modbus requests as a slave over the RS-232 port or the RS-485 port. It's simple, but requires a couple of rungs of logic using both an open function block and a Modbus slave function block. These function blocks are accessible in Cscape from the communication section of function blocks in your toolbox. The open function block is used to select what port you're using. You're going to configure baud rate, data bits, stat bits, etc. Are you using Modbus RTU or Modbus ASCII? The Modbus slave function block is specifically geared towards assigning a Modbus DID, which is between 1 and 247. You will also assign what's called a Modbus timeout, which is the amount of time that a Modbus slave will wait in between messages from a master before it determines that the master has gone away. It then takes corrective action, like turning outputs off, etc. Now let's take a look at how the variables in your program are mapped over to the OCS and ultimately to the Modbus register space. It depends on what style of logic you're using. If you're using the traditional register-based advanced ladder, every time you've created a variable, you've had to map it to a memory location. If it's on the table that I showed you just a minute ago, then every OCS register has a corresponding Modbus register, which you then use to access that data. However, if you're using a more modern approach, such as our tag-based advanced ladder or IEC logic, you've got to take the variables that you want to share over Modbus and map those to specific memory locations. You do that from the program variables table from the column marked tag, which at some point we're going to rename map. That shows that none of the top group of variables are mapped or tagged, so none of them are accessible over Modbus. Whereas the two on the bottom, process pressure and process temperature, have been mapped over to internal OCS register space, which means they are accessible over Modbus. Now let's talk about 16-bit versus 32-bit. You'll notice that second variable on the bottom, process temperature, is a real variable. We want to ensure the master on the other end will interpret that properly, so we've mapped it to register 1001. The real variable is stored in both 1001 and 1002. So the master will need to request 1001 with a length of registers of 2. It will then receive both of those words, and the master will have to assemble those and interpret them as a real value. As you individually map your variables to OCS register space so that they're available over Modbus, you don't need to map them to consecutive locations. However, if you do map them to consecutive locations, you can make things much more efficient, as your Modbus master can grab the data with much fewer messages. Alright, now let's talk about using the OCS as a master. When you're using the OCS as a Modbus master, you're going to be configuring what we call a Modbus scanner. It is effectively functionality in the OCS where it is going to be retrieving, reading, and writing Modbus data automatically in the background. There are different modes in which the OCS can perform this scanning or polling of Modbus data. It can be done automatically, where it's either scanning data as fast as it can, or it's scanning data periodically. You can also set up manual scanning, where a trigger bit or register is used to instigate the scan. You can enable or disable the protocol on the fly. You can close and reopen a port, which can help faulty systems in some instances. Let's talk about 32-bit data handling. You can adapt to slaves that handle 32-bit variables as a single register, as well as slaves that send the most significant word of 32-bit variables first. You can configure what style of addressing each slave you're talking to uses. And then we provide you with plenty of status information that you can read to keep track of what slaves are responding, what kind of error codes you're getting, etc. Now let's talk about different styles of Modbus addressing. The drive manufacturer on the left uses 5-digit addresses. The drive manufacturer to the right uses decimal-based offsets and their manual. We allow you to configure what style of addresses each slave uses. You don't have to convert from 5-digit addresses over to an offset, or vice versa. You can just enter the data that you want to read or write for that particular slave in its native documentation. So on the left, when we enter in the data to be read or written, we're just going to type in 40001, 30001, etc. With the data field on the right, we're going to access a decimal-based offset in conjunction with a function code, which makes it much easier for us to make an accurate conversion between an offset and an address. The other thing that's kind of cool is if you have two OCSs talking to each other over Modbus, you don't have to use Modbus addresses at all. You can configure that slave OCS or the master that's talking to the slave using native addressing. We've tried to be flexible so that you can configure the data that you want to read or write from the slave and with minimal errors. The last thing you're going to do is create a scan list of variables. For each slave, you're going to make a list of what data you want to read or write. Each item in the scan list can consist of up to 32 consecutive Modbus addresses that you want to read or write. The fewer the scan list entries, the faster your response time will be. There are some differences between using register-based advanced ladder or using tag-based or IEC approach. With register-based advanced ladder, in your local register you're going to type in a local OCS register number where that remote data is going to be read into or written from. With tag-based advanced ladder, the best way of handling that is to set up one or more variable arrays in order to access that data in a consecutive fashion. If you're grabbing data from a slave which is 32 bits in nature, like a float or a double integer, there's a 32-bit access checkbox that you want to check. When you're creating your scan list, there are multiple scan list entry types. Polled read reads the current value every time through the scan list. Polled read write does the same as read, but also writes when the value changes locally in the OCS. Polled read write init does the same as read write, but also writes the local OCS value to the slave on PowerUp. And then you've got triggered read and triggered write, where you can assign a specific trigger bit to initiate a read or a write. You can map Modbus directly to graphics objects on a screen. For Modbus registers that aren't needed elsewhere, they can be tied directly to a graphic object or data object on the screen. These registers will only be read and written when that screen is displayed. Let's talk about how the OCS polls Modbus slaves at runtime. The OCS starts by executing the scan list from the protocol configuration if the protocol is enabled. The scan list is executed sequentially, item by item. Once the scan list is complete, any Modbus registers tied directly to screen objects are scanned in sequence. If at any point read/write data changes, or if a write is triggered, the scan list is interrupted to perform the write. If at any point a message fails, the OCS will retry the message as configured. Other entries in the scan list will not be executed until the message succeeds or the problematic slave is taken offline. Slaves taken offline will be ignored until the reacquire time expires. Okay, now it's time for a Modbus TCP walkthrough. I've got an OCS and I want it to be able to act as a Modbus slave over a serial port. To enable Modbus slave over a serial port, you need to have two rungs that you create. One that utilizes the port open function block, and one that utilizes the Modbus slave function block. These both can be found from the COM operations section of the toolbox with all the instructions here. Here's the open COM port function, and here's the Modbus slave function. Now keep in mind, there's also a Modbus master function block that still works. It was the original way that we did Modbus master protocol, but today it's only really used in cases where an application engineer wants to strictly control every aspect of polling a slave or a series of slaves. However, this is an uncommon situation. Okay, so the OCS open function block. Alright, this is the configuration parameters for that. So which serial port am I using, and then what are my communication parameters? You're going to use Modbus RTU every chance you can, and half duplex multi-drop on every chance you can as well. So you'll set up those parameters, you'll have a coil that turns on when the port is successfully opened. A contact off that coil will also enable Modbus slave. And the only things to configure in this function block are the Modbus ID, which is going to be somewhere between 1 and 247, a timeout value in milliseconds, which is how long the slave is willing to wait for a master to poll it on a periodic basis, and if that master quits polling on that periodic basis, we'll get a flag in our status register that says the master went away. And then we can decide to take corrective action if necessary. Then we assign a single status register for monitoring back communications. So that's all that's required for setting up an OCS to be a slave on serial Modbus. I will now discuss using the OCS as a Modbus master, and specifically a Modbus TCP master, although the same configuration method applies to both. Alright, where do we configure an OCS to be? Well, let's start with a Modbus TCP slave. I've got an EXLW that I'm configuring. So we go to LAN1 IP config. In this case, I'm using Service Pack 3, which we'll talk about in a little bit. So I'm going to use DHCP to set up my Ethernet. I could have manually configured all these things, or used variables. But today, we're talking about Modbus TCP, not necessarily about setting up the rest of the Ethernet stuff. Okay, so if I want to be a Modbus TCP slave, All I do is check this checkbox under Resident Protocols called Modbus Slave. There are a couple of options I can configure, but usually I don't need to configure them. But I highlight that here and hit Configure Selected Protocol. I can switch to Modbus UDP if I want, but Modbus TCP is the most common, and that is what we will be using here. Here's the port that you more than likely won't change, and here's the ability to add a write inhibit bit. When it's on, we will not accept writing of data into our memory table. That's all that's required for configuring a Modbus slave. We can be a Modbus slave and a Modbus master with the same OCS. Let's show you how to do that here. Alright, we've already configured Modbus slave. Let's go down here under Downloadable Protocols and we select Modbus Client. Client and master are the same thing. We've got 3 levels of configuration that we're going to be able to do as a Modbus TCP master. Let's start on the network level. In the upper left hand corner, there is your minimum port ID, maximum port ID, and keep alive time. Generally, you don't need to mess with these things, the defaults are perfectly fine. Here is where you can select between Modbus TCP or Modbus UDP. We can be a UDP or a TCP master. Below that is where we configure our timeouts and our retries. If a master sends a message to a slave, it waits a certain amount of time for that slave to respond. If the slave is powered off, it's never going to respond, so we don't want to set the timeout too high. The default is 10 seconds, which is too high. If I was setting this up, I would set something closer to a second. In what case would I set a longer timeout? If I'm doing Modbus TCP over a complicated network that may even be going out over the internet, or if I'm over a cellular modem, I could have some occasional delays. In that rare scenario, I might want to bump it up above a second, but in all other cases, I would generally keep it at 1 second or even a bit shorter. So let's see the timeout here at 1 second. So when we send a message to a slave, if it doesn't respond within a second, then we assume it's not going to respond for that particular message, and we will retry. This here is how many times we will retry, anywhere between 0 and 255. The default is OK. This here, under the normal polling of a slave, is how long it will wait for it to respond, and how many times it will retry. Now let's say that it doesn't respond, and we do a retry, and it doesn't respond again. At that point, we will take the node offline. We will ignore that node until a reacquire time has expired. This is set up in milliseconds, and the default is 100 seconds. So going to ignore that slave and talk to other slaves, and then 100 seconds later, it's going to try and talk to that slave again. It would try twice because we've configured one retry, and if the retry fails again, then we take it offline again. So that's what the reacquire time is. Let's take a look at our scan configuration. The scan is a process in which the OCS is going to be reading and writing data to one or more slides on a periodic basis. If we set it up for the default of automatic, with an update interval of 0, that means we're going to be updating through that scan list as fast as possible. Most of you will probably use that setting. If you don't want it to be as fast as possible, you'll change your interval from 0 to a number of milliseconds. Or you can configure up a manual scan, which will be triggered with a variable. If you want to set it up that way, select manual and set up these variables for trigger and ID select. Then, this disable network is new for Service Pack 3. Its function is to take Modbus TCP down as a whole, which has the same effect as closing the Modbus TCP port, then reopening it again once it's re-enabled. You've got the ability to support up to 4 status registers or variables, which can give you feedback for things like turnaround time on the Modbus scan list, how many messages are going or are received, etc. The register for the event, the variable for disabling the network, which is 1 bit, and the variable for status, which is for 32-bit variables, are all optional. However, I highly encourage you to configure them. So that's the network level of configuration. Let's look at the device level of configuration. This is where we add information about the different slaves that we're going to talk to. Let's look at various configurations for each slave. Okay, so this slave is already configured. Firstly, I can give it a name. The name is used when I'm monitoring this configuration. In this case, it's set for slave 1. I've got a target IP address. I can hardcode the IP address like I've done here, or I can enter in a variable so that that can be configured from a screen. That's probably the ideal way of doing it, but in this case, it's hard-coded. The target port is configured here, which is almost always going to be 502, because that's the standard Modbus TCP port. If I want, I can assign a variable to that. Some Modbus TCP slaves require a unit ID that is more than just the IP address. In that case, you can check this checkbox and configure the slave ID somewhere between 1 and 247. This is where we configure the details for your specific slave that may misbehave a bit when it comes to handling 32-bit data. And then here is where we configure what style of addressing it uses. Then you've got a disable bit for that slave, which is new with Service Pack 3, and you've got a status register, which is 2 consecutive word type registers. If you want to stop talking to a slave when you get an error, you can select this checkbox down here, or you can go ahead and retry as you've configured. Alright, so that's configuration of an individual slave. We could have multiple slaves here, but in this case I'm showing one. The third level of configuration is the scan list. Here we specify what data we want to read or write, and we can set up a whole series of transactions that we want to occur. Let's go ahead and assume that we've got a slave number 1, that's the only slave I've configured, and I want to configure or access Modbus registers. Well, how do I enter that here? If I need to remember how to enter it, I can press this little help button. It tells us the format I need to enter it in, so I could easily add this in by looking at the user's manual for my device. The data I want might be starting at 40007, and I might want to read 6 consecutive registers here. Where do I put that in my local memory? I'm showing you how to utilize Modbus TCP with our tag-based ladder editor. I'm using tag-based variables. I'm going to go to the variable selector here. I've previously created something called slave1 holding registers. That's a variable that's in a RAID variable. So in this case, there's up to 32 different word type registers, all consecutive, from 0 to 31. I'm going to select the first one here, which is sub-0. What that means is my address registers 40007 through 40012 are going to be located or copied into slave holding registers sub-0 through sub-5. Okay, so I'm reading in 6 consecutive words. Here's where they're coming from, and here's where they're stored locally. If this is strictly a read, I'm going to leave that as a poll read. If I want to read it normally, but be able to write it when it changes, I can select a polled read/write. If I want the value of this in the OCS to be the one that's used on PowerUp, if there's a difference, I would select polled read/write in it. If I want a triggered read or triggered write, I'd select one of these over here. So that's configuring an item in the scan list. And here you can see I now have the local data, where it's coming from, how many words it is, and in this case, this little icon indicates it's a read-write. Okay. Last thing I'm going to show you live is how to directly add Modbus data from the screen. So I'm going to pull up the screen here. Let's go ahead and add a data object. Let's say that we want to be able to set the value that's in Modbus register 40001 with this data object, and maybe that correlates to motor speed. So instead of selecting internal register for my data source, I'm going to select slave1 etn1. So that tells me the name of the slave that I named when I configured the slave, and etn1 is telling me that's coming from Ethernet port number 1 or LAN 1. Now I'm going to type in my Modbus variable, and if I don't remember how to type those in, I can press this little help button here. So it could be 40001. Alright, and I'm just going to read it in one 16-bit value. I'll use a slightly larger font here, and it's going to be read/write. I'll give it a legend of motor speed. I'll just keep it simple. So now I've created a data field which directly accesses a Modbus variable from a Modbus slave, and it only accesses this data while this particular screen is being displayed at runtime. So if it's not being displayed at runtime, that data is not being normally read or written. And that concludes our demonstration. From a frequently asked questions standpoint, can an OCS be a Modbus TCP server and a Modbus TCP client at the same time? Absolutely. Can multiple Modbus TCP masters access the same OCS acting as a slave? Absolutely. Can the OCS support multiple Ethernet protocols at the same time, say Modbus, TCP, Ethernet IP, FTP, or email? Absolutely. We can support up to 16 simultaneous connections. Now, a couple things we can't do that I want to point out. We don't yet support a Modbus TCP write-only function. We also currently don't support any Modbus slave, TCP, or otherwise that require a non-standard Modbus ID between 248 and 255. We plan on adding support for these soon. Thank you for watching today's tutorial. The Q&A session will begin shortly.
Okay, thanks everybody. Got a couple of questions coming. So I'm being asked, my device says it supports Modbus slave. How do I know whether it's RTU or ASCII? Well, in that case, you can 99.9% guarantee that it will be RTU. Very few devices actually support ASCII, and certainly the ones I've seen that do have been from many years ago. So virtually every device now that says it supports Modbus is Modbus RTU. And then Modbus TCP/UDP, which is the most appropriate to use. Well, again, it all comes down to the device. Most devices will only support TCP, Modbus TCP, and not Modbus UDP. There is an advantage of using UDP in that it's slightly more efficient. The TCP insists on there being a connection between the host device and the server device. It establishes the connection before it starts transferring. With UDP, it just throws out requests and gets the answers back and uses that data. So it's slightly more efficient. The big advantage of TCP is that when you've got very large messages that are split across several packets, TCP will make sure that they arrive in the right order and they're reassembled properly. With Modbus communications, in one packet you can get 500 values, so there's no need to worry about the order that they're in. So UDP is appropriate, but the majority of devices, again, that support Modbus over Ethernet do so using TCP rather than UDP. Okay, so we've covered those. So let me drop to my screen. Basically, we've more webinars up and coming. So June the 10th, we're seeing here today, Modbus and Modbus TCP. Next week, you'll see we've got Getting Started with OCS. We've got Owner IO review and the ISV count review after that. If you want to register for any of those webinars, please do. You just click on the registration link in this page on our website. More webinars will be added as we move along, but certainly those are the next three scheduled. So if you're interested in any of those, please register and we'll see you there. Thank you very much for attending, everybody, today, and hopefully we'll see you at one of these upcoming webinars in the next few weeks. Thank you very much.